Hello, Advanced Digital Systems class. This is Dr. Morrison with guest student Bridget Roal today. I've had about three or four students come in and ask me the same question about the sign multiplication algorithm. And I think I've come up with a pretty simple way of conveying it. And so we've gotten a little bit of the way through. And I want to kind of record a video so that way all of you can review this and use it for your exam review. So the consistent themes that I'm seeing here are that some of the students are really struggling with converting binary numbers. And I always say, I will tell you that there's a 4-digit number, and that means it can be anywhere from 0 to 15 in positive, right? Mm-hmm. So the first thing is, I'll give you an example, like give me 4 times 7.
28.
So we know that's 28, right? We know it's 28. Yeah. But I always say, so what's the first step? And it's convert to binary. Mm-hmm. Now, when you've been dealing with it long enough, you're going to know that it's 0, 1, 0, 0, and that's 0, 1, 1, 1 for the two numbers. Mm-hmm. But everybody who's come into the office hours has a little bit of a struggle. Let me put this in single instead of double paragraph. Single. So how do we get you up to this point where you didn't really practice this that much? But when you get to a job interview or an exam, you will be expected to do this pretty rapidly. So, and poor Miss Roal, she's the one who's going to be asking the questions too. It's okay to get them wrong now. It's better to get them wrong now than on the exam, right? So, what is 2 to the 0?
0.
No, it's not 0. Everybody else who was in here made the mistake. It's okay.
Okay.
What is anything to the 0 power?
1.
1. Okay, so it's 1, right? So when it's a 4-digit number, that's 0, 0, 0, 1. Okay. Because we represent the 4 digits, right? This is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. And any kind of digital number is actually, if it's a 1, it's 1 times 2 to the 3, 0 times 2 to the 2, 1 times 2 to the 1, 0 times 2 to the 0. So that becomes 2 to 3, which is what?
8.
What's 2 to the 2?
4.
What's 2 to the 1?
2.
2 to the 0 is? 1. Very good. So now first things, if you know these numbers, if we go 0 is, of course, 0, 0, 0, 0. We know 2 to the 0 is 1. So therefore, we want to have 0, 0, 0, 1. If we know 2 to the 1 is 2, and I'm typing it out so it's more clear for everybody back in on the video. Like that, 0, 0, 1, 0, right? So 2 to the 2 is?
4.
4. And that becomes, what is it in binary?
0, 1, 0, 0.
Exactly right. And then 2 to the 3, you can probably tell me the whole pattern
1,
by now.
0, 0, 0.
Which is 8. I should actually watch the keyboard when I type. All right, so we have this pattern now. And this is the pattern. If you know these 5, you can figure it out from here on out. Mm-hmm. So the one that Bailey, I gave her earlier was 7. Mm-hmm. I just gave you the answer. So I say 7. So how do we figure this out if we don't know right off top of our head it's 0, 1, 1, 1? So first thing you do is you look for where the number is between. Well, 7 is between 4 and 8. Mm-hmm. So for those of you who are going to be taking algorithms for your computer engineering, this is kind of what's known as binary, cutting everything in half. So we have a range from 0 to 15, right? Mm-hmm. And then we cut it in half. So we know that's 8. So with 7, it's on that side, right? Mm-hmm. So then you cut it in half again, that's 4. Well, we know 7's in between 4 and 8. So now we know it's between 0, 1, 1, 1, 0, 0, 1, 0, 0, and 1, 0, 0, 0, right? So now it just becomes knowing some sort of smaller version of that number. So we know it's 0, 1, and then something else that we're adding to it, mm-hmm. right? So we know that 7 is 4 plus 3. Right. So, and what's 3 in binary?
0, 0, 1, 1.
Right, so we're just adding 1, 1 there. So now we have 7. So instead of having to do this thing, 7 divided by 2 is 3. Then we divide by 2 again. It's 1. 1 divided by 2 is 0. So that gives us 0, 1, 1, 0, 1, right? You just kind of know these basic numbers. So my recommendation starting out is to just practice that. So you kind of give yourself, if you're going to do these problems, give me sign multiplication or restoring or non-restoring division. There we go, much better. Just know the basic numbers and then kind of build off of that. So in this case, what I want to do is I'm going to give you 4 times 7. So what were the two terms that I gave for when we're multiplying two numbers together? What are those two numbers? On your sheet, you had are these abbreviations, right?
Yeah.
MCAND and MPlier.
Okay.
Right. So we're talking about the multiplicand and the multiplier.
Okay.
So when what we're actually doing, and the rest of you on the video weren't here, we were starting this stage where I said, explain to me how to do 15 times 12. So what I want Miss Roal, that's right, Roal, right? Roal, Miss Roal to do is I want her to do the same thing that she just did for me in here. And she's going to teach you how to do 15 times 12 like you learned in school. Now that she's actually went through it once. And so if you'd be so kind, please explain to the class what you did. Here, let me do tabs over. So, all right, so go ahead, let's go start.
Okay, so first you multiply the 5 times the 2, and that gives you 10. But you can't put 10 in that space, so you have to put the 0 on the bottom and carry the 1. And then you multiply 2 times 1, and that gives you 2. And so you have to write 2, and the 1, and then it's 3. And then after that, you have to add a 0 on the bottom, because you're going to add another number. And then 5 times 1 is 5. And 1 times 1 is 1, so you add that. And then you add those two numbers, so 30 plus 150 is 108.
Very good. Now, what you're doing, the whole point of this algorithm is to actually physically do what you were taught in kindergarten with binary logic, digital logic, advanced digital systems, right? So what Brittany did here is she first took a multiplicand and multiplier. So multiplier is a verb, right? So now you're combining your English and so the verb, what is multiplying? What actually you're doing is you're adding 15 12 times. So that makes 12 the verb, multiplier. If you recall from when I started out section 2, and I was talking about Hobbes' philosophy of arithmetic, where it's just either adding over and over again or subtracting over and over again. So that's why you have the divisor in your restoring and non-restoring division is, if you're doing 8 divided by 3, the divisor is 3 because that's your verb. It's a divisor, and now you have this. So what's actually going on here, if you think about it from everything else, so now we have our multiplicand and your multiplier. Now, if you recall from the algorithm that I specifically stated that, I'm sorry, this keeps happening, we should just go to single, that your multiplicand needed 2n plus 1 bits, and your multiplier needed n plus 1 bits. Now, you intuitively, when Brittany described how to do this, she intuitively did this correctly. Now, the challenge is explaining it right. So you all know this. You all know why you need 2n plus 1 for your multiplicand. And here's how you know it. Because when she did 15 times 12, right, she did 2 times 5, right? That's a 0. She carried the 1, and that gave 30. Then she did a bit shift. Adding this 0, you see how it's going left? That's when you look in the algorithm, it's shift left. You're shifting the multiplicand left. Because what you're actually doing when you're multiplying 15 times 12 here and you're multiplying this 1 here, What you're actually doing is multiplying 150 times 1. So it's 150 times 1, and that gives you 150, of course, which then you add to 30, you get 180. So what you're actually doing, this is your shift left. But Brittany also knew how to intuitively shift right on the multiplier, which is that part of the algorithm as well. Because what she is doing here is you have 15 times 12, and she knew to start with the least significant bit and multiply it. But then what she did is she went to the 1, right? Right, Brittany? So what you did is you did a shift right on the multiplier and made it now that became the least significant bit, and that became 0, 1. So what actually happened is she did 15 times 2 and got 30, right? And then you had the 0 here. So then she did a shift left of the multiplicand, which is 150, and then she did a shift right of the multiplier, so that became 0, 0, 1. And then she checked the least significant bit. It was a 1. She did it 150. Now, the reason why I said she also knew that intuitively you have to have 2n plus 1 bits, not just for the multiplicand, but for the product, is because you have to be able to represent your solution. Remember, this is advanced digital systems. You have to be able to actually numerically represent the result physically. So what she did is by doing the bit shift and providing the opportunity for 3 bits, she's actually doing 30 and 150. If we had just limited it to 2 bits, we would have had 80 with an overflow, and that would have been the problem. So providing 2n plus 1 bits provided the 180 and the space to be able to do the solution. So now, we now know how to do this. So actually what we can do is we can do 15 and 12 in binary. Because now we now know how to do this, both converting to digital, and we know how to represent the algorithm. So now we're just going to represent it the way I presented it in class. So just we're going to do the same steps. So I'll do it in 2 phases. One, we'll do 15 times 12 over here, which was, as we recall, it was 30, right? Let me get this over here. So, there we go. It's good enough. Better is the enemy of good enough, right? And so then you do the shift. You have the 0, right? And then that becomes 150. You add them together, and it becomes 180.
Right.
So how do we represent this digitally? Well, first step, I tell you, is to convert them to binary. So what's 15 in binary?
Well,
In 4-digit binary.
4 digits. Okay. Well, 8. Maybe we have to add.
So we have 8.
Okay. 8.
Mm-hmm.
Okay.
So 8 was 1, 0, 0.
And probably only 4.
Yeah, I did 4. So 8 plus 4 is 12. And so now, so we're not up to 15 yet.
3. So 1, 1.
Yep, there you go. So when you see 15 on an exam, remember 16 is 1, 2, 3, 4, 5, right? Because 16 is 2 to the 4,
Right.
and we start with 2 to the 0. So, and if you get any number that's 1 less, then you just remember it's all 1s before that. That's a good good hack there. So if it's 15, it's 1, 1, 1, 1. If it's 7, 7 is 8 minus 1, right?
Yeah.
So it
right.
becomes 0, 1, 1, 1. What's 3?
0, 0, 1, 1.
Like, stick to the same algorithm. What's 3?
4 minus 1.
4 minus 1, very good, right? So that just becomes 3, and 4 is 0, 1, 0, 0. So you just subtract, it's 0, 0, 1, 1. And then 1, of course, is just 2 minus 1, which is 1, right? So we have 15, which is 1, 1, 1, 1. So what is 12?
So 12 would be the same thing minus 2, so it'd be 1, 1, 0, 1.
No, if it's another thing, if it ends with a 1, it's an odd number.
Right. Well, he's right. So
1100.
yeah.
Yeah. So it's very simple. Just 8, 12 is between 8, 16, right?
Mm-hmm.
So it's somewhere in here. So now you just know you do 8 plus 4. So you know 4, this is 2 to the 2 is the third digit, 2 to the 0, 2 to the 1, 2 to the 2. So that's 15 times 12. So now we have our multiplier and multiplicand. And as Brittany correctly did when she taught it, you have to make your multiplicand 2n plus 1, right? Because that's where we're going to... So we have a sign bit. And then we make our multiplier n plus 1 to represent the sign.
Okay.
So what's the first stage in the algorithm before anything else? X or what?
X or
sign bits, right?
Yeah.
Now, why? Take a guess. Better be wrong now than on the exam, right? By the way, you did this intuitively when you were teaching the class about this too, right?
Right.
So when I gave you 15 times 12, did you say negative 180?
No.
Why not?
Because it's positive.
Because both numbers were positive, right?
Right.
So if I gave you negative 15 and negative 12, what would you give me?
Still positive.
Because you need exclusive OR.
So that way you don't get a negative.
Exactly. So exclusive OR, the logic is 0, 0. So we have A and B inputs, 0, 1, 1, 0, and 1, 1. You all remember truth tables, right?
Mm-hmm.
So F is the function A XOR B. Mm-hmm. So that's when I say XOR, it typically would also be representative as XOR, and it means exclusive OR. And what we mean by exclusive is in the instance where one of them is 1, but not both. Exclusively OR. So here, it's not exclusively OR because it's 0 or 0. Mm-hmm. So it's 0. 0 or 1, well, one of them is exclusively OR, so it's 1. One of these is exclusively OR as 1 as well. Both of these are 1, and that's 0. So if we had 15 times negative 12, it would be a negative number. If we had negative 15 times 12, it would be a negative number. Mm-hmm. If we had negative 15 times negative 12, it's a positive number. Mm-hmm. So that's why the first stage of the algorithm, we do step 0. That's why I call it step 0, so you're not doing anything else. So step 0 is XOR sign bits. And that means you had 0, and I can do a lot of copying here to help simplify this. And then we have this as well, so our product. So I'm going to put 2 tabs here just to separate them. And remember, we create so this was the multiplicand, and I created a product, right? That was 2n plus 1 as well in the algorithm, if you remember. And if you recall from you looking at the sheet, I had this as, let's see, where is it? Edits. I should be able to see here, home. So remember when I did this, I had that as red, right? Mm-hmm. The reason why I had that as red is because that's what's actually changing. So you could actually, on an exam, write this out, and in fact, I'll white out everything that you don't need to include. So step 1, just like Bridget said, we are going to do this 15 times 2, right? Mm-hmm. But instead what this actually is just 0, 1, 1, 1, 1, and 0, 1, 1, 0, 0. Now, I'm going to state this very clearly. You are not permitted to do this on the exam. You're not permitted to go 0, so you go 0, 0, 0, 0, and then you know what I'm saying here, like 0 with bit shift, and then doing this where you go 1, 1, 0, 0. Oh no, 1, 1, 1, 1. Like we were doing before. Mm-hmm. Do not do this on the exam. You will lose your points. Why? Because I'm not teaching you how to do kindergarten or whatever whenever you learn multiplication second, third grade. Mm-hmm. What I'm asking you with courses Advanced Digital Systems, I want you to demonstrate to me that you can know how the multiplication algorithm goes through the Advanced Digital System. That is why I'm having this table. That's why I'm setting it up. So we're going to represent it in a way that demonstrates that you know how the computer works, right? So step 1, we're going to check the least significant bit. So when I say check LSB, here you can, what's actually happening is you check this bit, right?
Mm-hmm.
And that's you're going like, okay, so this was a 0, which would be 0 times 0, 15, right? So it'd be 0, 0, then 150, and then you get 150 there. So the step 2, if it, if it is 1,
Mm-hmm.
then add the product to the multiplier, right? So we're going to add it over here, and that's going to give us, and you don't have to rewrite everything else. You get over here, this becomes 0, 0, 0, 0, 0, 1, 1, 0, 0, right? See how that worked? Because we're adding, I'm sorry, so we're adding 12 here.
Mm-hmm.
And so that allows us to go like that. And then now, not Bridget, not Stephanie, then you're going to left shift your product, right? Because that's what we did here. We left shifted the product, and that became 150, right? So that makes it, let me type this up properly, left shift implier, and that actually became 0. Oh, I'm sorry, canned. Sorry. I know you all are having so much fun watching me type. So then this became 1, 1, 0, right? Because you can actually see here this left shift. And then you want to right shift the multiplier, because what you're doing is you're now actually representing this 1 as that. So that's why I say step 4, right, or just do right shift implier. And that becomes 0, 0, 1, 1, 1.
Mm-hmm.
And then you can do the same thing, step 2. And for simplicity's sake, I'm just gonna copy this here. This became actually not what I wanted to place at all. Control C, Control V. So here you're checking the least significant bit,
Mm-hmm.
right? It's 1, then we're going to add this, so it becomes this number plus this number, right?
Mm-hmm.
So this became, and another student here says 0, let me make that smaller, 0, 0, 0, 0, 1, 1, 0, 0, right? 0. So you're adding, what's actually going on here, to make it look simpler, is you're actually going to take this number here and add them together. So you see here we're going to put this in the result. So the 1's fine. This becomes 1 and 1, 0. So that's the sum there. You carry the 1. This becomes 1, 1, 0. And then it becomes a 1 there. Does that make sense? So you're just adding. What you've actually done is you had 0, 1, 1, 0, 0.
Mm-hmm.
And then you added 1, 1, 0, 0, 0. 1, 0, 0, 1. Just
okay.
that.
Yes.
And so forth. So then you're going to left shift. And actually, for even better simplicity, I'm just going to put these together. I think you all got the idea. So keeping this separate. So then that allows me to go doot. And then, so that's your left shift. And then your right shift, this bit goes away. That gives you 1, 1, right?
Mm-hmm.
And then we're going to do this again. Step 1, we check it. It's a 1, right? So then you can even just say, you can even just circle it and go yes. To even, as long as you're indicating properly that you've checked it. So step 2, we're going to add them here. So now we're adding this number. Let me make this, and then this number. Actually, what I'm going to do is I'll put this over here, and then this number here, and then the result will just come out right where I want it to be, right? So now we have these two numbers, right? So then it becomes 1, 1, 0, and then carry the 1. Right? And then this can become white. That can become white there. See how it's working?
Mm-hmm.
And then we do our same thing. We're going to do step 3. We're going to left shift our multiplicand, so that becomes 0, 0, 1, 1, and then the rest zeros, right?
Mm-hmm.
And then step 4, we're going to right shift our multiplier, 0, 0, 0, 0, 1. One more iteration.
How do you know, like, I mean, we know how many iterations we need to go through because of this example, but, like, how do you know, in general, how many?
It's going to be the width of your multiplier. So you knew 15 times 12, you knew inherently you have to do it twice, right?
Mm-hmm.
So you do 0, 30, 0, 150, right?
Right.
So you knew 2 because this is 2.
Mm-hmm.
Whatever the number of inputs, so you have your ALU input.
Mm-hmm.
So when you said that, when you take your control signal, right, 4-bit control signals, you have A and B, and you said B is the multiplier. Whatever number of bits that go into your multiplier, that's going to be your number of iterations at the physical level. It's a very good question. Good. Okay, last but certainly not least, check the least significant bit. 1, right? Step 2, we're going to add them over here. So then we add this again. So we're going to be 0, 1. So this will be 1. Right.
Mm-hmm.
And then we shift left, shift right, and then you're done.
Okay.
Good
Makes
deal.
sense.
All right. So I'll post this on Blackboard.